Today we want to look at a few classical results in number theory: Fermat's little theorem, Euler's theorem, and Wilson's theorem. And I want to look at these from the point of view of group theory. There's a lot of different ways of proving these results, but I think group theory is the most natural way to view these theorems. So let's just start by reviewing a few results from group theory. So recall the order of a group is just the number of elements in the group, and we put the vertical bars around the group to denote the number of elements. We can also talk about the order of an element of a group, and I'll denote that ORD G, like this, order of G. Or if I want to specify what group I'm in, I'll put a subscript G. And it's just the smallest positive integer, such that g to the n power is the group identity element, which in this case I'm denoting as 1. Now, not every element has a finite order like that. If it doesn't, we just say the element has infinite order. In particular, if we're in the modular group GM, the group of units mod m, well, I'll write ORD sub m for the order of A mod m. So similarly, if A is an element of the integers with A relatively prime to m, the order mod m of A is then the minimal positive integer n such that A to the n is congruent to 1 mod m. So there's two different ways. We can talk about the order of an integer or the order of an element of this group GM, and it means the same thing. So what's the order of 2 mod 7? What power do you raise 2 to in order to get 1? And that's simply 3, since 2 cubed is 8, which is 1 mod 7. And it's the smallest exponent that would work. Or if I want the order of 2 mod 17, we first observe that 2 to the 4th is negative 1. And therefore squaring both sides, I would get 2 to the 8th is equal to 1. And clearly no smaller power would work, because 2 squared cannot be 1, because 2 to the 4th is negative 1. And 2 to the 4th doesn't equal negative 1. So any smaller power would have to be a divisor of 8 itself. Okay, Lagrange's theorem states what? It says that if you're in a finite group, and H is a subgroup of G, then the cardinality of H is a divisor of the cardinality of G. And the way to think about it is just in terms of a coset decomposition. So if G is a finite group, you can express G as a disjoint union. So you might put little dots. It means these cosets are non-overlapping. And being a finite group, there'd be a finite number of cosets of the subgroup H. And then you observe that every coset has the same cardinality as H itself, because there's this one-to-one correspondence between elements of the coset and elements of H. So H times xi just corresponds with the element H. Therefore, since this is a disjoint union of cosets, the total number of elements in G, we just add up the number of elements in these k different cosets, and we get k times the cardinality of H. And therefore, the cardinality of H is a divisor of the cardinality of G. Now it follows from Lagrange's theorem that we get the following. If G is a finite group, little g is an element of G, then little g has finite order, and its order is a divisor of the group order. Okay, so first of all, why does G have finite order? And we'll just consider the sequence. We just take different powers of G. G g squared, g cubed, etc. Well, this is a finite group, and so we can't have infinitely many distinct objects in the sequence. So since g is finite, there exists some integers j less than k with g to the j equaling g to the k. And then by cancellation, j is the smaller one, we would get 1 is g to the k minus j. And therefore there's some positive power of g given us 1, which says g has finite order. Okay, next. I want to show that the order is a divisor of the order of the group G. So let's let n be the order of G. Well then, the group generated by G is just 1, G, G squared, and you keep going until we hit 1 again. So you go all the way up to g to the n minus 1, and then the first time we hit 1 is when I hit g to the nth, and then we've just cycled all the way back to the beginning. And so we see that the order of this group is equal to n. And then by Lagrange's theorem, n must therefore be a divisor of the group order. Next theorem. If G is an element of finite order in a group G, capital G, and m is an integer with g to the m equaling 1, then the order of G must be a divisor of m. And conversely, if the order of G is a divisor of m, then g to the m is equal to 1. So we get an if and only if statement. Proof. So let's let, I don't have an n here, n be the order of G. Okay. And suppose that m is an integer with g to the m equaling 1. So we'll just prove one direction. And I want to prove that the order of G is a divisor of m. So, well, it makes sense if you just think of the cycling around. But if we want to write a formal proof, I would use the division algorithm, let's say. So by division algorithm, m is qn plus r, where r is an integer between 0 and n. Okay, and g to the m equaling 1 would imply that g to the qn plus r equals 1. And let's write that as g to the n q times g to the r. But what's g to the n? N is the order of g, so that's 1. Aha! We have another power of g equaling the identity, and that power is strictly smaller than n, which is the minimal positive number that would give me the identity. Therefore, by minimality of n, we must have r equals 0. Thus, if r is 0, m is a multiple of n. Conversely, suppose n is a divisor of m. This is the easy direction. Say kn equals m for some integer k. Then g to the m power is g to the kn, which is g to the n k times, and g to the n is the identity. So this is just equal to 1. Next theorem. If G is a finite group and little g is an element of capital G, then if I take little g and I raise it to the order of the group that it's living in, that's the identity. And, well, this is just putting a couple things together. So let n be the order of little g. And so we proved a theorem that says this exists. That there is some exponent that gives us 1, and not only does it exist, it's a divisor of the group order. Well, okay, so that was the couple lemmas ago. Then we just proved a lemma that says if n is a divisor of the group order, then g raised to this order must equal 1. Thus, by proceeding lemma, let's double check that that was, yeah, this is the lemma that tells us when do you get the identity. You get the identity if the order of the element is a divisor of the exponent. And in this problem, the exponent is the order of capital G. And really, that's a generalization of Fermat's theorem and Euler's theorem. That's all it is. If you're in a finite group and you take an element of the group and you raise it to the group order, you'll always get the identity. So let's see how Euler's theorem is connected to this. Euler's theorem says the following. Take any modulus m, any positive integer m, and any integer a with a relatively prime to m, then a raised to the Euler phi function of m is congruent to 1 mod m. So all we do is we think of working in the ring Zm, and I'll let a bar be an element of Zm, and since a is relatively prime to m, a bar will be a unit. So I could have said a bar is just an element of the group of units. And what is the group of units mod m? It's an abelian group. It's a finite group with how many elements? Gm is a group with phi of m elements. And so we're in a group. We have an element a bar. The previous lemma tells us what? This by previous lemma, a bar raised to the group order, which in this case is the Euler phi function, is the identity. And now we just translate that back to a congruence. A to the phi of m is congruent to 1 mod m. Fermat's little theorem is just a special case of Euler's theorem. It's the special case where the modulus is a prime. So this time you take any integer relatively prime to p. That just means an integer not divisible by p. And you'd get a to the p minus 1 is congruent to 1 mod p. And the proof, all we need to say, it's special case of Euler. Just note that the Euler phi function of a prime is p minus 1. Wilson's theorem. Wilson's theorem says the following. For any prime p, p minus 1 factorial is congruent to negative 1 mod p. P minus 1 factorial is congruent to negative 1 mod p. And it's an immediate consequence of the following lemma. If p is a prime and x is an integer with x squared congruent to 1 mod p, then x is congruent to plus or minus 1 mod p. Okay, so x squared congruent to 1 mod p is equivalent to saying that p is a divisor of x squared minus 1, which is equivalent to saying p is a divisor of x minus 1 times x plus 1, which is equivalent, since p is a prime, to saying p is either a divisor of x minus 1 or it's a divisor of x plus 1. And in the first case, that means that x is congruent to plus 1. In the second case, it's congruent to negative 1. All right, let's look at the proof of Wilson's theorem. So let p be a prime. Then p minus 1 factorial is just p minus 1 times p minus 2 times p minus 3 times 3 times 2 times 1. And the trick here, let's go ahead and make it a congruence, is to pair each number in that product with its multiplicative inverse. So pair each number a with a between 1 and p minus 1 with its multiplicative inverse. And when you do that, so you'll have an a would be one of these values, maybe p minus 3, and then somewhere in the list would be a inverse. And so you rearrange the product to group these two terms together and say, well, that's congruent to 1. Those two terms will just cancel out. And so you might think to yourself, well, then everything would cancel out here because everything has a multiplicative inverse, leaving you with an answer of 1. And yet the theorem says the answer should be negative 1. So what's going on there? Well, there are two elements whose multiplicative inverse is the same as the element you're starting with. Those are the elements we treated in the previous lemma. So saying that x squared equals 1 is equivalent to saying that x is the multiplicative inverse of itself. And the only elements that have their own multiplicative inverse are plus and minus 1. So over here, when we rearrange these terms, we would be left with this first term, which is the negative 1, and then we would have a 1 for all of the other pairs that group together, and we would have the last term 1 sitting at the end. and then p minus 1 is just congruent to negative 1. Okay. I want to give you another way to prove Fermat's little theorem, and it's going to follow from the pth power binomial identity, which says the following. If x and y are variables, then x plus y to the pth power is congruent to x to the p plus y to the p. So in particular, you could plug in any two integers for x and y, and that would be a true statement. So it's kind of like a dream theorem for beginning algebra students. To raise a binomial to a power, you just bring the power into each term and you add it. And you can forget about all of the cross terms you would get by FOILing it out. Now this generalizes in an obvious manner using induction. A sum of n numbers to a pth power is the sum of the pth powers mod p. So this result is only true for primes. As you'll see, there's an important divisibility property that primes have. The key lemma is the following. If p is a prime and k is any value between 1 and strictly less than p, then p is a divisor of the binomial coefficient, p choose k. So I think the most elegant way of proving this is to use acute identity for the binomial coefficient, and you can check this out by just writing down the definition with factorials. So p choose k is p divided by k times p minus 1 choose k minus 1. So try that out for size. Therefore, if I put the k, just get rid of the denominator, k pk equals p times p minus 1 k minus 1. Now this is an integer right here. It's a whole number. And so we're saying that p is therefore a divisor of the left-hand side. P times some integer equals this left-hand side. But k is strictly less than p, so p is not a divisor of k. And so p must be a divisor of p choose k. So how do we use that? Well, if you use the binomial expansion, x plus y to the pth power is x to the p plus p choose 1, x to the p minus 1y, p choose 2, all the way down the road until you hit y to the p. And then you just observe, aha, all of the binomial coefficients have a factor of p in them. So mod p, these terms are all 0. Plus 0, plus 0. And the only term that survives is the term y to the p, together with the first term right here. And that's all there is to it. And then I'll let you think about writing a formal proof. It just follows by induction the second part of the theorem. So how do we get another proof of Fermat's little theorem? So that n be a natural number. Okay. Then n is just 1 plus 1 plus 1 n times. And so if I want to look at n to the pth power, that's just 1 plus 1 plus 1 to the pth power. Okay, now I use the second part of the lemma, which would say, well, that's congruent to 1 to the p plus 1 to the p plus 1 to the p, mod p. Well, 1 to the p is just 1. And how many 1s am I adding up? I'm adding up n 1s. So I've proven a more general version of Fermat's little theorem. So we have established that n to the p power is always congruent to n mod p. Now I just did it for positive integers, but it's trivial to then deduce that it's going to be true for negative integers as well as 0. So this is in fact true for all integers. In particular, if p is not a divisor of n, you can just cancel out. Then by cancellation, we get n to the p minus 1 is congruent to 1, which is the more traditional way of stating Fermat's little theorem.